Well, the undesirable oxidative reactions in red wines, of course, result in a loss of color, as one would expect. Can also cause a change in color from red to brown. And if it proceeds far enough, you can get the formation of brown color deposits. White wine browning, and also the formation of deposits in extreme cases. But one of the most undesirable effects, of course, of oxidation is the acquisition by the wine of both an oxidized taste and odor. Now, there are a large number of factors that affect oxidation. Grape variety, region where grown, degree of maturity which the grape is harvested, presence or absence of enzymes, temperature, pH, oxygen, sulfur dioxide, grapeseed tannin, tannic acid, copper and iron, citric acid, tartaric acid, sunlight, sugar, acetaldehyde, and the type of phenolic material. That's not on your list. So add type of phenolic material. Most of the menu handed out to you gives the examples of the effect of most of these substances I've just enumerated. In Table 1, the varietal order of susceptibility to browning. We devised a standard browning test consisting of storing the wines at 120 degrees Fahrenheit with a great excess of oxygen, or I should say air, and then observing the increase in the browning of the wines. And of some 20-odd varieties of white grapes, that is wines from white grapes that we worked with, we found that the Pinot Blanc was the worst of the lot. That under our test conditions, 100% of all the Pinot Blancs that we tested became excessively dark. Full Blanche 50% and Thompson Seedless 25%. As I think I mentioned in an earlier lecture, if you want to use the best grape possible from the standpoint of resistant oxidation, make all your white wines out of Thompson Seedless. Now, the effective region, that is the climatic region where the grape is grown. You can see there that region 2, we worked with 19 varieties of grapes. Region 2, a cool region, 30.6% of the wines became excessively dark. Region 4, Davis's example, of course, of region 4, Lodi, 58% became exceedingly dark. So, as a general rule, the warmer the region, the more danger of the wines oxidizing. Maturity, the riper the grape, the greater the susceptibility. And now as to enzymes. The polyphenol oxidase enzyme is naturally present in the grape. And it can cause very fast browning. Last year, Mr. O ran some rather extensive tests on the rate of browning of different grape varieties, as the juice from different grape varieties. And he found that when he was bubbling air into the juice, that he could not raise the oxygen content because the enzyme was reacting so rapidly that it was using the oxygen as fast as it bubbled into the juice. So that's why it's absolutely essential in handling whites, particularly, that the sulfur dioxide be introduced at the crusher, at the must pump. He also found that as a general rule, 75 parts per million of sulfur dioxide would inactivate the enzyme, but occasionally 100 parts per million of sulfur dioxide was required. So if you want to be on the safe side, again, I recommend you add 100 parts per million of sulfur dioxide at the crusher for the sole purpose of inactivating the polyphenol oxidase and preventing browning. We've also done a lot of work on browning in wines, various factors, conditions, and so on. We've never been able to demonstrate the presence of polyphenol oxidase in the fermented wine. So that is not a factor in wines themselves. It's only in the juice and in the fermenting liquid up to some unknown point in the fermentation. That's also why we recommend cleaning the juice prior to fermentation, because The enzyme is associated with the particulate matter that's in suspension in the juice, that is the pulp, skin, and that sort of thing. And if you rack your juice, or even better centrifuge, you get rid of these particles, then you're going to remove the last danger of oxidation from polyphenol oxidase. Because the SO2, of course, will only react with the enzyme that it can reach. And enzymes inside the particles and can later on be released during fermentation could cause browning. The effective temperature and browning rate, we worked the 15 different wines. And going from 20 degrees centigrade to 35 degrees centigrade, we increased the rate of browning 9 times. So you can see that temperature is a very important factor. Going from 35 to 45 degrees centigrade, only increased it 2.5 times, and about the same going from 45 to 55 degrees centigrade. So over the range of 20 to 35 degrees centigrade, the lower the temperature, the much more protection you have against oxidation. pH is a very, very important factor. We took a large number of wines. You can see about 120 wines. Divide them up according to pH. We had 45 wines on average pH of 3.14, and only 17.8% of these became excessively dark. 53 wines on average pH of 3.48, and the percent became excessively dark was just about double that at 3.14. And again doubled when we went to 3.88. The 70% of the wines become excessively dark. So that's why I say the pH is a very, very important factor in the susceptibility or the resistance of wines to browning or darkening. The lower the pH, the more resistant the wine. Next table shows the effect of oxygen on browning. We did not put oxygen in the bottle. We calculated the amount of oxygen in the headspace in the bottle. In other words, this is aerobic oxygen, 21% oxygen in the air that's in the bottle. With 60 milliliters of oxygen per liter available, it only took 8 days for the wines to brown. With 8 milliliters, 47 days, 6 milliliters, 138 days, and 4 milliliters of oxygen, 173 days. So you can see why it's very important that you minimize the amount of oxygen that's available to the wine. Yes?
Is that milliliters of oxygen per liter of wine?
Per liter of wine. Amount of oxygen is available to a liter of wine. That's why it's so important when you're bottling wines in particular to decrease the head space to the greatest extent possible, or even better to use a vacuum filler where a partial vacuum is pulled and the cork is inserted. Because with poorly designed bottles and no attempt made to purge the bottle prior to filling, it's possible to get as much as 12 milliliters of oxygen per liter available to the wine. And you can see that 12 milliliters took 14 days for the wines to brown. 4 milliliters took 173 days for the wines to brown. So that emphasizes the importance of minimizing the amount of oxygen that's available to the wine, particularly at the time of bottling. Yes?
What temperature was that done?
Pardon?
What temperature was that done?
This is all done at 120 degrees. It's a fast test, so-called fast test. The 173 days is not very fast.
What's the criteria for saying the wine was brown, particularly?
An increase of 0.150 optical density. An arbitrary figure. We arrived at that because in testing a large number of wines, we found that on the average, if we increased the optical density of 0.150, they became too dark to be commercially acceptable. So that's why we arrived at this 0.150 optical density increase, and this was a 20 millimeter light path.
We're kept at 120 degrees the whole time?
Yes. Sulfur dioxide, of course, reduces the rate of aldehyde formation, but on the other hand, it promotes its accumulation because it'll combine with it and form the bisulfite aldehyde complex and will accumulate the aldehyde as it is formed by oxidation. Now, effective SO2, we consider SO2 to be an antioxidant. It is an antioxidant. We look at the data given there in Table 6. We have 50 parts per million of total SO2 and 5 parts per million of free. In the presence of 12 milliliters of available oxygen per liter of wine, it took 14 days for this particular wine to brown. We greatly increased the dosage to 150 parts per million of total, 50 parts per million of free, but we only doubled the number of days required for this particular wine to brown. So you can see from that it tends to protect the wine from oxidation, but the presence of free SO2 in wine is not sufficient to make the dissolved oxygen disappear immediately. So all SO2 does is delay the oxidation rather than to prevent it. It'll take longer for your wine to brown to a given degree, but it will not prevent the wine from eventually browning as long as the oxygen is available. We're also interested in the effect of tannic acid because at one time it is fairly common practice to add tannic acid. In fact, at one time it's fairly common practice to add grapeseed tannin. But as you've been told before, grapeseed tannin usage was barred in the United States because back in the 30s and early 40s, too many of the wineries were using it to make what appeared to be old white wines very quickly because it would make the muscatels and that type of wine nice golden brown color, indicating a great deal of age, and you might have a wine that's only a few months old. So the federal authorities said this is deception of the consumer. You're forbidden to use grapeseed tannin. However, we still experimented with the effect of grapeseed tannin and tannic acid, and we found that with the control wine, the optical density increase is 0.090. With grapeseed tannin, that was decreased to about a third, to 0.037. In other words, the grapeseed tannin contains some antioxidant factor. The tannic acid, on the other hand, increased the browning rate, going from 0.090 to 0.140. So if you're considering only the oxidative effect, you would not add tannic acid to white wines because it will increase the oxidation rate rather than decrease it. Copper and iron, of course, are positive catalysts of oxidation. And Table 8 gives the effect of copper and iron. This is in the presence of 600 milliliters of oxygen per liter, which of course is a tremendous amount of available oxygen per liter. We want to exaggerate the conditions to see the effect of copper and iron where there is a great excess of oxygen available. On the control wine, 0 copper, 0 iron, it took 700 hours for the wines to brown. Where we added 0.3 of a part per million of copper, the browning time was reduced to 590. Where we added 4 parts per million of copper, the browning time is reduced to 560. Where we added 5 parts per million of iron, the browning time is reduced from 700 to 370 hours, and where we added 10 parts, it is reduced from 700 to 300 hours. So in the presence of unlimited oxygen, iron is the principal catalyst of oxidation, or browning. And with a limited amount of air, I don't give you data to prove this, but you'll have to take my word for it. With a limited amount of oxygen, copper is the main catalyst for browning. Now the effect of citric acid. It's common practice to add citric acid as a chelating agent for iron, as insurance against the possibility of iron casting, iron phosphate clouding. We took a wine, made available 60 milliliters of oxygen per liter, and had a series of wines over the range of 0 to 40 parts per million of iron. Adding 2 pounds of citric acid per 1,000 gallons decreased the browning from 4 to 8% over that range of 0 to 40 parts per million of iron. And the addition of 5 pounds of citric acid per 1,000 gallons reduced the browning from 10 to 13%. So we can deduce from this that the complexing power of citric acid is sufficiently great to partially inhibit the catalytic effect of iron. It's a significant inhibition, but it's not a major inhibition. So you cannot rely on the addition of citric acid to remove the catalytic browning effect of iron.
Was that 10 to 13 or 10 to 31?
10 to 31, I'm sorry. Tartaric acid decreased the rate of aldehyde formation, and as one would expect, the presence of sunlight greatly increases the rate of oxygen consumption. If you want to brown a wine in a great hurry, put it out in the sunlight in a white bottle and give plenty of head space, and it'll brown overnight. Sugar has only a minor effect. Its effect mainly comes from its binding power for SO2, but the binding power of sugar compared to acetaldehyde is less than 1% as much SO2 bound by sugar as is bound by acetaldehyde. So it has only a minor effect as far as oxidation is concerned. Acetaldehyde, of course, has a major effect because it's a great binder of SO2. Now, any questions on anything I've covered so far?
The maturity of the grape, if the grape is ripe but not, the skin is not broken or anything like that, would that increase the browning? You said just ripeness.
Yes, if you were,
Whole grapes?
we harvested grapes over the Brix range of 16 up to, well, I think one case we got up as high as 28. And by plotting all of the different harvest maturities versus the rate of browning, we got practically a straight line with a tremendous high degree of correlation. And without exception, well, I say without exception, there are a few exceptions, of course, but you can take it as a general rule that the riper the grape, even from 16 on up, the greater the tendency to browning.
Was there any attempt to measure the polyphenol oxidase?
No, not at that time. We do know that the polyphenol oxidase is greatly increased if the grape is damaged. If it's bruised, the amount of polyphenol oxidase increases drastically.
Do we know what role the polyphenol oxidase plays in an undamaged grape or any kind of fruit? Why is it there?
Why is it there? I don't know the biogenesis of polyphenol oxidase. Anyone enlighten us on that? No biochemists here? Or no one claiming to be a biochemist? I'm definitely not. Any other questions? I mentioned at the start of the lecture that the type of phenolic material was also a factor in browning. And it's probably one of the major reasons for the variation among wines to susceptibility to browning. If we were to take all wines, if they were all of the same pH, we would still find a great variation in the susceptibility of these wines to browning. And outside of the amount of polyphenol oxidase which is present, and usually there's enough there to react with the normal amount of oxygen that's going to get into the juice, the main reason for the difference in susceptibility is due to the type and amount of the various polyphenolic substances that are present in the grape. Now, if you look at this next table here, you'll see that we used 3 tannin fractions, the condensed tannins. In other words, those are actually tannins. They are polymers, fairly large polymers of tannins. That's why they're called condensed tannins. If you spot them on paper, they will not move. They'll stay at the origin. The other fractions are leucoanthocyanins. Those are the tannin fractions that can be converted to red pigment by oxidation in the presence of acid. And the catechins are the most numerous fraction ordinarily, and they are primarily monomers. And this table shows the effect of the polyphenol oxidase on the phenolic fraction. In other words, we took each one of these fractions, measured the amount of tannin that is present, and treated them with the polyphenol oxidase, and then measured the decrease in the amount of tannin. And that is shown as phenols precipitated as milligrams per liter. So you see the condensed tannins, the polyphenol oxidase precipitated 237 milligrams per liter. Of the leucanthocyanins precipitated 369, and of the catechins 1,371. So this shows very clearly that the catechins are the main substrate for the browning. If you were able to remove the major fraction of the catechins, then your wines would not brown if they had no sugar present. And that is the basis for the next table showing the effect of nylon treatment on the browning rate. This is nylon 66, specially activated by dissolving formic acid and precipitating out with methyl alcohol. And we added various amounts of nylon per 100 milliliters of wine, ranging from 0 up to a half a gram per 100 milliliters of wine. And then we measured the time required for an increase in optical density of 0.150. With the control, it took 51 hours, and where we added a half a gram of nylon per 100 milliliters of wine, it took 95 hours. So we practically doubled the length of time that the wine required to reach a certain degree of browning by treating it with a half a gram of nylon per 100 milliliters. Well, nylon was the first one that was available to us for this type of work for removing phenolics outside of the old organic agents like casein and so on, which we would found to be ineffective in removing enough phenolics to make any difference in browning rate. This is encouraging. Later on, PVP or PVPP, polyvinyl pyrrolidone, became available. So we made a comparative test between nylon and polyvinyl pyrrolidone. And you can see that the grams of gallic acid equivalent per 100 grams of resin. With nylon on the condensed tannins, 2.8, PVP 1.5. With leucanthocyanins, 10.5 nylon, 25% PVP. And with catechins, 7.5% versus 19%. This is the amount that is removed. So you can see the PVP is much more efficient, much more effective in removing catechins, the major substrate for the browning, than is nylon. And this has since been proven in practice. In fact, it is fairly standard, or I should not say standard, but it's fairly widely used practice, or practice followed, of adding PVP to fermenting white juice to remove the catechin fraction, that is, to a certain extent, to come up with a normal colored wine rather than one that is browner than desired. And PVP treatment can also be used following fermentation, after the wine is made, but it must be used with a great deal of care, because we found that sometimes the use of the addition of PVP to wines, particularly to sherries, will strip out the desirable characteristics and expose all the undesirable ones.
Is it odors, desirable odors? Or
Right. We did some work with standard baked sherry because we wanted to determine the feasibility of using a column stripping and then regenerate the column again. So one of the wineries offered us their facilities and gave us a small tank of sherry to work with, and we put it through the column, and it really lightened up the sherry beautifully. But oh Lord, how that stuff really stunk. Well, Caputi and Peterson did quite a lot of work at Gallo on this browning, particularly the effect of PVP, nylon, and so on. And these results are given in this table are pretty well substantiated by their work. They found that the nylon treatment was helpful in some cases and increased browning in others, but PVP was always helpful. The addition of PVP always decreased browning. Now, there are two types of browning reactions: oxidative and non-oxidative. The oxidative reaction, the primary oxidative reaction, of course, is the reaction with catechin, the oxidation of catechin. And that's the one that gives us the main problem with white wines. It's the oxidation of catechin. The other one is the reaction between sugars and amino acids. In other words, the Maillard reaction. And that is only a factor where you have a considerable amount of sugar present and the wine is stored for a considerable length of time at an elevated temperature. It requires many, many years at room temperature for any appreciable color to form as a result of the Maillard reaction, which of course is not true of the color formation by oxidation of catechins. That occurs readily at room temperature. Any questions? Well, I'd like to devote the rest of the time to a discussion of mainly of the mechanisms of oxidation. One of the first reasonable explanations of oxidation in wine was given by Professor Ribio Gaillon of the University of Bordeaux. I think it's in 1932, if I remember correctly, he published his doctoral dissertation on the oxidation occurring in wines. And he came up with an explanation that was substantiated by his experimental data. And for many, many years, this is the only explanation we had, and it's still good as far as it has gone. He explained the oxidative changes that occurred in wine in the absence of free dissolved oxygen. In other words, he could not measure any free dissolved oxygen in wine, and yet he was able to demonstrate that oxidation was occurring. And he explained this on the basis of the presence in wine of what he called intermediate oxidizing agents. And these agents have a greater oxidizing power than molecular oxygen. In other words, the oxygen that's present in the air. They'll oxidize substances that the molecular oxygen will not touch. Two of these substances are ferric, iron, and cupric, copper. In fact, those are the main ones. There are others, but those are the main ones. And these are further subdivided into two types of oxidizing agents. Strong oxidizing agents, ferric, which exist only in the presence of oxygen. And of course, the weak agents, cupric, which exists in the absence of oxygen. In other words, dissolved oxygen. And you can prove this for your own satisfaction if you want to by completely stripping a wine of the heavy metals copper and iron and you'll find that it's almost impossible to brown that wine to any extent, even in the presence of a lot of oxygen. Because molecular oxygen itself is a very, very poor oxidizing agent. It requires some catalyst to allow it to attack these substances which are fairly resistant to molecular oxygen. Well, this is the mechanism we worked with for many years. Then more recently, within the last, if I remember rightly, 8 to 10 years, 2 chemists engaged in research on browning and beer in France. Came up with an explanation for browning that is occurring in beer. Chapone and urine. That's called the Chapone urine mechanism. They developed a very elegant procedure for measuring oxidation occurring in beer. And they did this by following the rate of disappearance of ascorbic acid. Because it's you can use a colorimetric reaction to measure the amount of ascorbic acid. It's a very, very fast reaction. So that can be used to measure the rate of disappearance of ascorbic acid. And since ascorbic acid is a strong reducing agent that is itself is easily oxidized, it is the ideal substance for them to work with. Well, they found that the rate varied between beers. Not surprisingly, we know that the rate of oxidation varies tremendously between wines. So the rate between beers varied. They found that the catalytic activity of the beer did not remain constant with time. The catalytic activity does not remain constant with time. And surprisingly, they found that the catalytic activity was not directly proportional to the amount of iron and copper. As they measured the amount of iron and copper, they found that the catalytic activity, the rate of disappearance of ascorbic acid, which was their measure of oxidation or catalytic activity, the rate of disappearance is not proportional to the amount of iron and copper. Continuing the work, they found the reason for that. They found that only ionic copper was effective as a catalyst, and only complexed iron was effective. So in addition to measuring the amount of copper and the amount of iron, they had to determine the amount of copper which is free, that was in the ionic form, and they had to determine the amount of copper which is complex, or the amount of iron which is complex, to have a measure of the catalytic activity of the beer. Having gone this far, they continued their work, and they noted that in changing ascorbic acid to dehydroascorbic, which of course is the oxidation reaction, ascorbic acid being oxidized to dehydroascorbic, they used two times the amount of oxygen that is required for that reaction to occur. And this resulted in their finding that the oxidation of ascorbic acid was accompanied by the oxidation of an equivalent amount of organic substances that were present. So, in oxidizing ascorbic acid to dehydroascorbic, the amount of oxygen used for that reaction, an equal amount of oxygen was also used to oxidize other organic materials that are present in the beer. And that's the phenomenon that's known as coupled oxidation. And of course, in this coupled oxidation, the coupled system acts as a powerful oxidant. It'll oxidize substances that molecular oxygen will not touch. And that's a good reason for not using ascorbic acid in wines. I'll get to that later. Anyway, if you look at the mimeograph, the last page, it shows the postulated reaction, postulated by Chapon and urine. AH2, the symbol for, in this case, ascorbic acid, is reacted with 2 moles of the catalyst, in this case copper. The ascorbic acid is oxidized with the liberation of hydrogen and the reduction of the catalyst copper. In the reduced copper reacts with the 2 hydrogens plus oxygen to again oxidize the copper and to produce hydrogen peroxide. Then the oxidized copper must react with some reducing substances present in the wine, and of course ascorbic acid is a reducing substance among others, to reduce the copper and produce the radical, whatever radical is the reducing substance is. Then the reduced copper reacts with the peroxide to again oxidize the copper, form the OH, and the OH with the dot prime, which is the oxidizing agent. That's called the Fenton reaction. And that OH is the most powerful oxidizing agent that we have available in the organic system. And they are so strong that they do not differentiate between strong and weak reducing compounds. In other words, they will touch weak reducing compounds that molecular oxygen will not even begin to touch. Now this reaction, of course, is greatly slowed by SO2 because SO2 will react with peroxide. Though SO2 will not completely inhibit it because the reaction between the SO2 and peroxide is not that fast. And if you want to prove that to yourself, add 150 parts per million of SO2 to wine and add peroxide equivalent to molar equivalent to oxidizing it, and you'll find after a period of time that you can still pick up peroxide, and you can still pick up SO2. Now the rate of this reaction, if you do not have any SO2 to interfere with the rate, is dependent upon that third step. In other words, depend upon the amount of reducing substance that you have present. So the rate of the reaction will vary from wine to wine depending upon the amount of reducing substances that are present in the wine. And they prove that by adding free peroxide to beer, let it stand for 24 hours, and we're still able to analyze and find free peroxide. And we have no reason to believe that these same reactions do not occur in wine. In fact, we think that the chances are probably 99.9 to 1 that this is one of the main reactions that occurs in wine in browning. Now, Professor Cruz, who was active for very, very many years at Berkeley, and the predecessor of the Food Science and Technology Department, the old Fruit Division, later on the Department of Food Science and Technology, We started working on wine and other problems in about 1918, if I remember rightly, or 1914. Did quite a lot of work on the possible usage of ascorbic acid and other reducing agents, particularly ascorbic acid, as an oxidation protector of wines. He stored dry white wine with, let's see, 500 and 1,000 parts per million of ascorbic acid. At around 85 degrees Fahrenheit. After a few months, the ascorbic treated wines, these are stored in well-filled, tightly sealed bottles. He took no pains to strip the wine of air prior to the filling, but he did fill the bottles well filled and tightly sealed. And after a few months, the ascorbic treated wines were very much darker than the controls, and eventually they became almost black. In fact, he sent me some of the samples because he knew I was interested in oxidation, and it's one of the most striking examples I've ever seen of the possible bad effects of adding ascorbic acid to wine. Ascorbic acid, of course, has been recommended as an antioxidant in beers and wines. In fact, I think it's used to some extent in beers. It's used to some extent in Europe in wines. As far as I know, it's not used to any extent in wines in California. Because the net reaction is a conversion for every equivalent of ascorbic acid. It'll cause the disappearance of half an equivalent of dissolved oxygen, oxidizing it to water. So it's a good way to remove dissolved oxygen from wine. Just add ascorbic acid, and for every equivalent of ascorbic acid, you remove a half equivalent of dissolved oxygen. And therefore, it would reduce the amount of oxidation which could be accomplished by molecular oxygen. However, as we showed on these reactions, for every half an equivalent of oxygen that is oxidized to water, another equivalent of half equivalent of oxygen is oxidized to peroxide. And that's exactly what occurred in this experiment with Professor Cruz's. They formed peroxide, and this reacted substance in the wine, browned it, and eventually made it almost completely black. Now, as long as you have free SO2 present, this oxidation, or this coupled reaction, will be fairly minor. As long as you have free SO2 present, because the SO2 will react with the peroxide and will largely prevent its oxidative action on the other constituents in the wine. But once the free SO2 is used up and with this Fenton reaction proceeds, then you will get the undesirable browning and eventual blackening of the wines. And that's why we don't recommend the use of ascorbic acid as an oxidation inhibitor or oxygen scavenger in wines. By the way, this is a rather elegant method for removing unwanted SO2 from wines. 176 milligrams of ascorbic acid. Added to wine, aerated, will remove 64 milligrams of sulfur dioxide. Theoretically, it doesn't always work. Sometimes it does, sometimes it doesn't. Pardon? Total. Well, it has to go through the freeze stage for the reaction, but this is just a total, measured as total SO2. Well, in addition to the oxidation of these polyphenolic substances, you can have other browning reactions in wine besides the Maillard reaction, the sugar amino acid reaction. For example, if you have a fair amount of acetaldehyde, it can polymerize and form brown-colored compounds. Acetaldehyde can also combine with other phenolic materials to form brown-colored compounds. But the main source of the browning reactions in wines, to the best of our knowledge, is the oxidation of the phenolic materials, particularly the catechins. So acetaldehyde can be a factor, particularly in high acetaldehyde wines. Well, what we can do to increase oxidative stability? Use the most resistant grape varieties. That is where you have a choice. And again, if you have a choice, use the grapes grown in the cooler regions. Because you remember, the grapes grown in region 2 were much more resistant to browning than the grapes grown in region 4. And don't use overripe grapes. And add 75 to 100 parts per million of SO2 at the crusher and get a thorough mixture there, because that will stop the polyphenol oxidase, largely stop it at least. Also, cool your juice, settle and rack before fermentation, or better yet, centrifuge to get rid of the particulate matter. Store your wines at 55 degrees, maintain 100-150 parts per million of SO2 in wines. Maintain the least amount that will maintain your wines in the right condition. Keep the acetaldehyde content low, keep iron and copper content low. Add 1 to 2 pounds of citric acid. And minimize oxygen pickup. You can use inline nitrogen sparging, nitrogen and carbon dioxide blanketing, bulk storage, bottle purging, and vacuum corking. All of these things help. Keep the bottled wine out of sunlight. And lastly, if necessary, treat the wine with PVP. Any questions? Yes?
Yeah, this coupled reaction that you were talking about, is there an absolute requirement for ascorbic acid, or are there other reducing agents?
There are natural reducing agents present in wine.
Beg pardon?
There are natural reducing agents present in wine.
That serve the same function?
Right, because you don't have to add ascorbic acid to make the reaction go.
What is in wine sparging?
Where you put a device in a wine line that allows the introduction of nitrogen in very, very fine bubbles into the wine as it flows past the device.
Is this better than sparging in a large tank?
Oh, much better, much more efficient. Any other questions?
Well, do the heavy metal ions catalyze what might be some of the desirable oxidative reactions?
Oh, there's a lot in literature about desirable action, but it's never been proven. Okay, that's it.